Okay, so welcome to section 7.5, and this section is dealing with operations of radicals. So just like we can add, subtract, multiply, divide, simplify, do all the different algebra and arithmetic to other expressions as we have throughout the course of the year, we can also do them with expressions that contain radicals. Okay, this section has a lot of different procedures in it. That's why it's split up into two different videos. This first video is going to deal with the basics, just the simplifying and the simple operations, okay? There's a lot in it. I'm not going to lie to you there. So please take your time watching it. Rewind things if you need to. Pause as you're going through the different practice problems in your notes. And be sure to ask me questions in class. We will do a lot more practice with this in class, but I want to have this video both so you can get some exposure to it prior to class as well as after class to prepare for quizzes and tests and the like, okay? Because this is a very crucial concept dealing with radicals. It's not that challenging, but it could be new to you and it could get a little picky. You got to be very attentive to what's going on. Okay, so the first thing we want to do is we want to simplify radicals. Now, in the last section, 7.4, when we dealt with nth roots, we basically dealt with radicals that, what I like to say, are kind of the easy ones. They're always perfect squares or perfect cubes or perfect fourth powers. Well, now we're going to work with radicals that aren't necessarily perfect. And the way we do that, and as we've done in the past, and I'm sure you've done in Algebra 1, you just break down each of the radicands into their prime factors, and then you use the index, which is, remember, the little number at kind of like the check mark of the radical, and if there is no index, as in the case of the first example, we automatically assume it's a square root. That index tells you how many of a kind you need in order to pull the group out of the radical. Okay, so let's do an example. 32x to the 8th, the square root. So when we do our factoring of 32, we get that 32 is 2 to the 5th. So 2 times 2 times 2 times 2 times 2. And then we have our x to the 8th. Since it's a square root, we're going to be pairing up like numbers. So I have a pair of 2's and a second pair of 2's. So each pair of 2's comes out of my radical and gets multiplied together to be a 4 on the outside. Okay, now let's work with the x's. I have x to the 8th, so I basically have 8 x's, and I could write that out, but I would run out of space on my PowerPoint. I'm taking the square root of x to the 8th. Well, remember when we deal with powers of variables, they're a lot easier to simplify. You just do the power of the radicand divided by the index, and if it divides evenly, in this case, you have x to the 4th on the outside. Remember, if there was a remainder, that would be what would stay on the inside of the radical, which we'll do in some other examples. So I take 4x to the 4th out, and I am left with just a 2 on the inside to correspond to that 5th 2 in the factors of 32 that didn't have a pairing. All right, let's do the same thing with the next example. Now I have a cube root of 27y to the 12th, z to the 7th. Okay, so let's factor the 27. 27 is 3 times 3 times 3. What do you know? That is a perfect cube. So my cube root says I take a group of 3 out of the radicals. So I have 3 3's. It becomes just one number 3 on the outside of my radical. Y to the 12th. 12 divided by 3 is 4 with no leftover. So y to the 4th goes to the outside, and all the y's will disappear from inside the radical. Now z to the 7th. 7 does not divide evenly by 3. 7 divided by 3 is 2, and I have a remainder of 1. So I have that z to the 1st still inside the radical that didn't have a group of 3 to come out with it. All right, we could do the same thing with a 4th root. The 4th root of 162, a to the 6th, b to the 13th, c. So we'll start with 162. All right, so if you need to, you can use a factor tree. 162, that's 2 and 81. 81 is 9 and 9, and then each 9 is a pair of 3's. Okay, 2 times 3 times 3 times 3 times 3. By the way, I've talked about this before, but when you want to deal with factors of large numbers, on your Inspire, remember there is a command. You can simply type in the word factor and then put 162 in the parentheses, and then it will output 2 times 3 to the 4th, so you don't have to do that factoring tree if you don't want to. All right? Okay, back to the problem, though. We still have to deal with the letters as well. So I have it factored out. I see that there is one foursome of 3's. They're going to come out of the radical. The 2 will stay in. So I'll start with the numbers there. Now we'll deal with the powers of a. I have 6 a's. I can only take them out 4 at a time. I can take out one group of 4 a's, but then I have 2 left. B to the 13th. Okay, 13 divided by 4 is going to be 3, but again, I only have 1 left, so I have to keep that b inside. And then the c, there isn't enough to take out any c's, so the c just stays inside. All right, so remember, the key idea is groups go to the outside, leftovers stay inside. Okay, and if you have multiple groups, as in the case of that first example, you multiply them all together. All right, try some examples on your own. Pause the tape now, pause the video now, and then pick up for the next operation. Okay, next we're going to do multiplication of radicals. Okay, the big idea with multiplying radicals and really most operations with radicals, outside numbers and inside numbers are always going to keep themselves separate from each other. So for multiplying radicals, we're going to multiply outside numbers if applicable and the inside numbers separate, and then simplify the one new radical that's formed. So for this first problem, root 10 times root 5, we simply multiply 10 and 5 and we get 50, and now we're just left with breaking down the square root of 50. So the square root of 50, it's going to be 5 times 2, so the pair of 5s come out and the 2 stays in. Okay? Now if there's already numbers on the outside, as in the second example here, we multiply them together. So 2 times 4 gets me 8. And then we multiply our radicands. So 3 times 12 is 36. X times x squared is x cubed. Y cubed times y to the 5th is y to the 8th. And then we just break that down. So the square root of 36 is 6. So we do the 6 times the 8 that's already out there. The square root of x cubed, I have 1x on the inside. Another x, excuse me, 1x that goes on the outside for the pair of x's. And then that third x stays inside. And then y to the 8th splits itself up into 4 groups, so I have y to the 4th on the outside. And then all I have left to do is multiply these two numbers, 48x y to the 4th root x. Okay, let's do an example of a higher indexed root. Cube root of 3x times the cube root of 72x to the 5th. Again, we multiply the insides. So 3 times 72 gets me 216. And then x times x to the 5th is x to the 6th. 216 is a perfect cube. That's 6 times 6 times 6. So the 6 can come out. And then the cube root of x to the 6th is x squared. Okay? When you have a perfect, just like we did in the last section, where everything comes out, that radical sign disappears. We would never write an empty radical. It would just be 6x squared. Okay? So again, the key idea is multiply your outsides and your insides separately and then simplify the one single radical that's left over as the product. Okay, you can pause the video now, or you can rewatch these examples if you need to, and then move on to the practice. All right, now let's talk about dividing radicals. Same idea. Okay, inside and outside numbers get divided separately and then simplified. The property that's at work here from your book is called the quotient property. Basically, just that means, and we've talked about this before when we dealt with taking square roots in the quadratics chapter. Essentially, if you take the square root or any root of a fraction, it's like taking that root from the numerator and then dividing it by the same indexed root of the denominator. So the nth root of a over b is just the nth root of a over the nth root of b. So here's some examples of that. All right, so 4 root 15 over 2 root 3. We divide the outside numbers and we get 2. 15 goes into 3 5 times. 2 root 5. 5's a prime number. Can't break it down anymore. Done. Next example. Negative 12 root 24 over 3 root 8. Again, divide the outside numbers. That's negative 4. The inside numbers, 24 divided by 8 is 3. 3 works out to be prime. Done. Don't have to do anything else. Cube root of 64 over the cube root of 4. All right, so again, 64 divided by 4, that is going to be 16, cube root of 16. But 16 can get split up. 16 is 2 times 2 times 2 times 2, 2 to the 4th. So I've got the cube root of 2 times 2 times 2 times 2. I'll take out one group of 3 2's, put it on the outside. That fourth 2 stays inside. So this reduces to 2 cube root 2. Okay? You have a couple examples similar to this in the notes. Pause it if you need to rewatch. I know I went through this rather quickly, but it is just the basic ones are just dividing the outsides, dividing the insides, and then reducing if necessary, like in the last example. All right, well, what if everything's not as pretty as that last slide? What if the outside numbers maybe don't divide, or rather, what if the inside numbers don't divide? Well, then you have to do what's called rationalize the denominator. And we talked about this a little bit when we were dealing with complex numbers in Chapter 5. And I told you we would do this again in the square root chapter. So here it is. Essentially, all you're going to do, we don't like square roots in denominators, the same way we didn't like I in denominators. The way we get rid of that is we multiply top and bottom by essentially a radical that's going to make that bottom become a perfect square or a perfect cube if it was a cube root, and so on and so forth. So here's some examples. So for the first one, I've got 14 over 2 root 3. Well, the outside numbers can still reduce, so we'll do that first. We get 7 over root 3. But my final answer here has a radical. So to get rid of that, I multiply top and bottom by square root 3. Okay, I can do that because square root of 3 divided by the square root of 3 is essentially a fancy way of writing the number 1. And remember, from the very beginning of the year, if you multiply a number by 1, it keeps its value, the identity property. That's what we're doing here. Okay, 7 times the square root of 3 is 7 root 3. Root 3 times root 3 is root 9, but what do you know now? That's a perfect square. So 7 root 3 over 3 is how we would reduce it. And now there's no denominator. That has a radical. If you went to your calculator and typed that in, 7 over root 3, and got a decimal, and typed 7 root 3 divided by 3, you should get the same decimal, assuming you put parentheses in the right spots. All right, next one, root 5 over root 8. Okay, so first thing I see is the square root of 8 can get split up. Let's rewrite that as 2 root 2 to make our work a little bit easier. Hasn't gotten rid of the radical in the denominator, but now I have to just work with smaller numbers. So to get rid of the square root 2, I multiply the whole fraction by root 2 over root 2. That gets me root 10 over 2 root 4, which now gets me root 10 over 4, because I have 2 times the square root of 4, which is 2, so that's where the 4 comes from. Root 10 over 4. All right, let's try the next one. Root 27 over 12, rather. Well, let's do the property from the last slide, and let's split it up into 2 separate radicals so we can reduce them. All right, the square root of 27 is 3 root 3. The square root of 12 is 2 root 3, because 27 is 3 times 3 times 3, and 12 is 2 times 2 times 3. So a pair of 2's come out of the bottom, and a pair of 3's come out of the top radical. Now look at this. The root 3's cancel. So where it looked like I started with a denominator that contained a radical, by simplifying the roots separately, I end up not having to worry about rationalizing my denominator. I could end up with a nice rational answer of 3/2. All right, for the last example, 8 over 3 root 5. Again, I've got a radical in that denominator, that root 5. I want to get it out, so if I multiply both the top and the bottom of the fraction by the square root of 5, I get 8 root 5 over 3 root 25. The square root of 25 is just 5, so I get 8 root 5 over 3 times 5, which is 15. I don't have to reduce any further. Notice, the 5 and the 15 don't reduce because one's inside a radical and one's outside a radical. As I said earlier in the video, inside numbers and outside numbers never get along in problems. Okay? The only thing that we could reduce would be the 8 and the 15, but since they're not reducible, we stop. All right, take a couple minutes. I have some rationalized examples. Give those a try before we move into the next and final set of operations. All right, we've done multiply, we've done divide, we've done some nasty divide with the rationalizing the denominator. Now we're going to do add and subtract. Okay, if you can simplify a problem like 3x plus 5x, you can simplify addition and subtraction of radicals. Remember, when we add two expressions that contain variables, we combine like terms. So for the problem that I just posed here, we'd get 8x. We wouldn't do anything with the x's. We wouldn't make it x squared. We wouldn't touch them. We'd only add the numbers in front. We're going to do the same thing with radicals. Instead of combining like terms, the key is combining like radicals. And what I mean by like radicals, I mean same index and same radicand. So, D, not T. So in these two examples I have of combining like radicals, 3 root 2 and negative 2 root 2 are like radicals because they both have a root 2 as their radicands. Another example, 5x times the cube root of 4 and negative 3 times the cube root of 4 are like radicals because they have the same index, they're cube roots, and they're cube roots of the same value, 4. The 2 root 2 and 4 cube root 2 are not like radicals because one's a square root and one's a cube root. Be very careful about that, okay? 2 root 3 and 2 root 2 are also not like radicals because even though they have 2's in front, they don't have the same number inside. All right? So when we combine like radicals, all that means is we add the outside numbers together. So in the first example, root 2 plus 3 root 2 minus 5 root 2. They're all like radicals because they're all something times the square root of 2. So all we're going to do is add the outside numbers together. I have 1 plus 3 minus 5 is negative 1. So this simplifies to be negative root 2. We can do this in a problem with more than one radicand. Again, we just combine the like ones. So 5 root 3 and negative 4 root 3 are like radicals, and we're left with the square root of 3 for that pairing. 7 root 2 and negative 2 root 2 combine to get me positive 5 root 2. I cannot add any further. Do not add any further. Stop here. It is possible that we can end up with final answers that contain more than one radical, and that's absolutely fine. All right? Now look at these next two examples. The radicands are a little bit bigger. None of them are the same. So you might think you can't do it. But if you look closely, most of these radicals have perfect squares in them. So we have to simplify each radical individually and then try to combine like terms. So the square root of 45, well 45 is 9 and 5. So this is going to be 3 root 5. There's already a 3 out here, so we multiply them together and we get 9 root 5. All right, 80. Okay, well 80 is 8 and 10. 8, I've got 3 2's. 10 is another 2 and a 5. So I take out 2 pairs of 2's. We multiply them with the 5 that's already there. 5 times 2 is 10, times another 2 is 20. So negative 20 root 5. And then 4 times the square root of 20. 20 is 4 and 5. There's a pair of 2's here. Multiply them with the 4 that's already there. Gets me 8 root 5. Now look at that. By simplifying all of my individual radicals, I do have a bunch of like radicals now. These all end up being root 5's. So we can combine all our numbers. 9 minus 20 is negative 11. Plus 8 is negative 3 root 5. And that's my answer there. Okay, let's try one more. Again, these don't look like radicals, but I'm going to guess that once we break down 12, 32, and 72, we'll end up getting some like radicals. Okay, well 12, that's going to be 2 root 3. There's already a 9 out here, so we'll multiply that and get 18 root 3. 32, all right, that's 8 and 4. 2, 2, 2 for the 8, another pair of 2's for the 4. Okay, so it looks like I have 2 pairs of 2's that are coming out, times the 5 that's already there, gets me 20 root 2. And then 72, that's going to be 2 and 36. 36 is 6 and 6. The pairs of 6's can come out, so minus 6 root 2. So in this case, I have one odd man out root 3, but the root 2's can combine, so our final answer will be 18 root 3 plus 14 root 2. Okay? Take a few minutes, rewatch any section that you need to rewatch, jot down any questions that you might have. If I went through something a little bit quickly, please ask me about it in class. Please try the addition and subtraction examples in your notes. We will do a lot more with this in class, but this gives you a nice little taste of the different operations we can do with radicals. Okay, so thank you for watching. I know there was a lot in this video, but I appreciate you sticking with it till the end, and have a